So I wanted to talk about coming up with the stresses on an inclined surface. So let's say that we take a specimen here that is in axial tension, and it could be in compression also. Eventually we'll talk about what happens if it's in a torsional load with shear and whatnot. We'll get to that later today. But the question comes up is, if instead of taking this x-axis that is at a right angle, that's at a normal to the axis, if we rotate the plane, so I'm going to come up with a direction x prime and y prime. Of course, x prime and y prime are perpendicular, but I'm rotating this x prime up some angle theta from that direction x. So what I'm going to do in doing that is I'm going to cut across that surface there at that angle. So you can imagine if you were to cut across there at that angle, like that, and I'd still have this force down here, P, and then I'm going to have a couple of forces, that's one that's on this surface here, like that, and one that is like that. Of course, those are going to resolve into the original value P, so that this thing is in equilibrium. And if I talk about these, I could say that this one would be, if I were to resolve it, that's going to be P times the cosine of theta, whereas this one here would be P times the sine of theta. And then I also have to account for this area. The area here, we could say A sub theta is going to be equal to the original area, A, divided by the cosine of theta. You could imagine that these areas, if I were to look at the original area A, if it was a square cross-section, it would probably look something like that. And then I've sliced it at an angle, so when we talk about A theta, it probably looks something like that, doesn't it? I mean, I don't know if you've gone into these little knick-knack shops and whatnot, and you see these wood plaques that are elliptical like this, and they have the wood grain like this. They have them at, you go to a place and they'll have that with an interesting expression. And I think some people think that trees grow like that. Probably not necessarily true. How do you get a plaque like that? I mean, Mother's Day's coming up. Maybe you need to make something, some handicraft here to try and, get back in some good graces. How can you do it? Well, if you slice it like this, what kind of a cross-section are you going to get? You're going to get that, aren't you? Okay, so how do you get this thing? Slice it like that, right? Okay, so when we slice it at that angle, we get a lot more area. So I need to take that into account, and I'll account for that as A divided by cosine theta. So when I look at this then, if I look at the stress in the y prime direction, I'm going to talk about sigma in the y prime direction. So that's in this direction here. And I could say that that's equal to P times the cosine of theta divided by the area. Remember, stress is always just force over area, so I take the force, P cosine theta, divided by the area, which we said was going to now be A divided by cosine theta. And if I tidy that up a bit, I have P divided by A times cosine squared theta. And that cleans up pretty nicely. Now, I need to talk about the shear stress that's going to develop here. I could talk about tau on the y prime face in the x prime direction. So that would have to do with that force right there. So we could say that that is P times the sine of theta, and then I have to divide that by the area because both normal stress and shear stress is force over area. So I'll divide by the area, A cosine theta, and here then I get, when I clean that up, P over A times sine theta times cosine theta, and we could probably use a trig identity on that. There'd be nothing wrong with this, but we'd probably clean it up a little more and say that we have 1/2 times P over A times sine of 2 theta. Might be a little tidier to look at. Okay, so those are those new values there. So what I'd like to see is the implication of that. And let me go to the next page. So what I'm doing here is I was initially looking at an element that looks like that, and then I've said, well, I'm going to rotate that element. So initially I had an element that looked like this and was probably pretty well behaved, had a normal stress on it. Sigma was equal to the force P divided by the area A. And then I came along and I rotated that, and I said, well, what happens when I rotate this? Okay, and I'm going to say that this is rotated at some angle theta. So I've rotated that at some angle theta. It's important that we recognize that. And I've come up with the value here in this direction. We found that was the sigma, so that's P divided by A times cosine squared theta. And then I've come up with the shear stress, which I could represent like this. And that's going to be, that shear stress is going to be P divided by A times sine theta cosine theta. Or I could say that it was, of course, that 1/2 times P over A times the sine of 2 theta. Now, there's actually another stress in here if I were to look in the x direction instead of the y direction, and you can just take the y direction and add 90 degrees to it, because then you'll get the x direction. If you add 90 degrees to that cosine, you'll get the sine, so we could say that this one, if we wanted to, was P over A times sine squared theta if we wanted to. Well, what I'd like to do is then look at the implications of that in terms of a graph. So let me graph these, where I have this angle theta, and I'm going to look at my stresses here. Okay, and when theta is equal to 0, this is theta equal to 0 degrees. This is, I guess, for lack of a better descriptor, theta is not equal to 0 degrees. But if theta is equal to 0 degrees, we get a maximum normal stress. So if I go from minus 90 to positive 90, I'm going to come up with something that looks like that. Seems to make sense. We get our maximum normal stress right there. And that has a value of P divided by A. Now, if I look at the shear then, so this equation, this curve here is for P divided by A times the cosine squared theta. If I look at the shear, it's going to do something like this at minus 45 and plus 45. I'll have something that looks like that, where it comes up to a maximum value that's going to be what? 1/2 P over A. Okay, from that expression right there. And this is, of course, then that 1/2 P over A times sine 2 theta, which is the shear stress, isn't it? Okay. So it's kind of interesting what happens is when we have this specimen that is under tension, okay, we've got this is what we started out with, it's under tension. When we look at an element like that, indeed it looks like that. It looks like tension, and we get that maximum stress, what we started talking about on the first day when we talked about stress, that normal stress there is equal to P over A. But if we look here, if we rotate what we're looking at, we actually get some shear stress, don't we? So there's actually shear in this example. And just because we don't look doesn't mean that it doesn't exist, right? I mean, if we build a place up at the North Pole, and just because we don't look out the window doesn't mean that there are not polar bears up there, right? Okay, so if you rotate this element, you will start to have shear. And in fact, if you rotate this element to 45 degrees, you'll get a maximum. We could say maximum shear at 45 degrees. Which brings us to an important point, a lot of times if you look at how things will fail, so if we take a, let's say a specimen like this, maybe it's square in cross section, and I'll put it under compression. Okay. And if you keep this distance short enough, if this is a short enough distance, it won't buckle. So we're not going to talk about buckling till the very end of the term. But what this will look like in failure is it'll actually slump down like this. Okay. And you can get it to do that. If you take a piece of wood and it's short enough and you soak it in a little bit of water, you can actually get it to fail like that. And it'll fail, and this angle is usually 45 degrees. Okay, because that's where you get the maximum shear. This happens all the time in concrete. They'll take concrete specimens. They take a cylinder of concrete, and they then test it once it's cured under certain conditions and for so long. They'll test it, and when it fails, it looks something like this. Okay, it's probably going to go the other way. I didn't do very good on that picture. So, yeah, that's an usher. Okay, so I need to get this going the right way here. There we go. Now we're back in the realm of possible. Okay, so you'll have something that looks like that. And a lot of times these cracks and whatnot will end up at 45 degrees. It's because the concrete is probably very adept at handling compressive stresses, but maybe not so well in handling shear stresses. And those of you that then go on to concrete structural talk about putting some reinforcing bar in there or something to start to handle those. So things like this that we would think would fail in a compressive fashion actually fail in a shear fashion. And it's because of this that if you look at a different orientation, if we look at the stresses at a 45-degree orientation, we start to get shear in there. You might say, well, how do you know where you're going to get the maximum values? Well, we're not going to spend too much time worrying about these equations. Oh, we'll do an example or two and things like that. But really, we're going to answer a lot more questions with Moore's circle. It's going to allow us to look at a lot of these in one fell swoop, rather than having to poke around at this angle and that angle. So we'll be talking more about this, but this is a good first step towards that. Questions with that? So let's try, as I mentioned, an example. So let's say we go back to some of our work from last time, and we fit this bar in between two fixed supports, and I look at, I'm going to look at a plane here. I'm going to say that this is 60 degrees. Say that this is the PQ plane. And we're going to heat this thing. We're going to say that delta T is 132 degrees F. That coefficient of thermal expansion is 6.5 times 10 to the minus 6, 1 over degrees Fahrenheit. And E is equal to 30 times 10 to the 6 psi. And what we'd like to do is we'd like to find then the normal stress, sigma, and the shear stress, tau, on that PQ interface, that PQ line. Okay. So what kind of material is this based on those numbers? It looks like it's probably steel, doesn't it? Okay, if it was closer to about 12 or 13 on the alpha, I think aluminum. Certainly this aluminum is going to be lower on E I think both these numbers fit steel pretty well. So it's probably steel. Well, we just got finished up that we said that sigma at some angle theta was equal to what? P over A times the cosine squared theta. And that tau at some angle was equal to, what do we have? P over A times sine theta cosine theta, or you could have 1/2 times sine 2 theta. These are the equations in general. Now the one thing we have to be careful of is we got to go back and look at how that theta was derived. So if we talk about how we started today, the angle was based off of the normal direction, the perpendicular direction. Whereas I've based this angle here off of the axial direction, haven't I? So what's theta going to be in this thing? If I were to put this normal direction in here, this is now theta, isn't it? So what's theta equal to? Theta had better be what? 30 degrees, right? I mean, we could go back through the derivation with this angle defined this way, but it's probably easier to redefine our angle with 30 degrees and use the equations that we have already derived. Well, remember from our work last time, this is really a statically indeterminate problem. And we find out that we went through the statically indeterminate process, and we said that delta was equal to, for the thermal effects, is alpha delta T times L. And that's also then this, one of these fixed supports pushing back is going to be PL over AE, right? We probably should have a negative sign because we have compression in there. And that allowed us then to show, we could say from last time, that P over A, that the stress, which is P over A, is equal to E times alpha times delta T, right? And we should probably put a negative in here because it's going to be compressive, isn't it? So if I go through this, I could solve for that P over A. I don't have to worry about the angle yet because I'm just looking at the normal plane. So we could say then that P over A is equal to minus E alpha delta T, which is negative, what's E? 30 times 10 to the 6 psi times alpha, which is 6.5 times 10 to the minus 6. Oh, those should be nice numbers. Times delta T, which is 132 degrees F. This is 1 over degrees F, so those cancel, and I get psi in the answer, which is good. That turns out to be equal to minus 25,740 psi. Questions with that so far? So we could have done that yesterday if we wanted to. Now today, let's see if we can get this. So sigma for the PQ plane or interface there is going to be equal to what? Well, I take this value here, minus 25,740, and I'm going to multiply it by cosine squared of 30 degrees, right? Which gives me minus 19,305. I got too many significant figures, but so you can see where it comes from. PSI. So that value is actually less. This one, in fact, is the maximum. If we were most worried about axial stress, we'd look at that one. This one we're going to recognize as less. But while this is the maximum for the normal stress, it doesn't have any shear stress at that orientation. The shear stress at this PQ orientation, though, is certainly not a zero value. We'd have minus 25,740 times the sine of 30 times the cosine of 30, or if you wanted to, you said 1/2 times the sine of 2 times 30. Get the same answer, and that's minus 11,100 46 psi. And again, I've got too many significant figures, but so you can check your work with it. I'll leave that. So if we had something that didn't support shear very well, this might be a real problem, right? Yeah, could be a real problem. And I think you've got a homework problem that takes you through this. I think it has a solder joint or a glue joint that's at an angle. A lot of times they'll do that to get more surface area. Classic one is a finger joint. If you look at finger jointed wood, they cut it like this, right? You glue it together so you get more surface area. So you could talk about the stress on those inclined surfaces if you wanted to. A lot to be learned from gluing things together, glue joints, making models. We'll talk about some of that, or you get some experience with some of that in the bridge design. I had a friend at college, I think he got kind of bored. He used to take his desk chair and up to the top of the dorm and throw it off, and then go down in the street below and collect up all the pieces and glue them back together, and then do it again and again. So anyway, he got good at gluing things back together. His chair didn't look like it had suffered any damage, so it was always kind of interesting. Other questions? Yeah. Got to have a hobby, yeah. Yeah, destructive testing. Yeah. So we're going to move along to the next section here, which deals with torque. Okay, and we've talked about this before. If you have, let's say, maybe the shaft of a screwdriver, and it's engaged in I mean, this is essentially then fixed here, and you're applying some torque to this, or maybe you've got the extension in a socket set. Let's see if I can draw this. So that would be fixed, and you're maybe applying a torque to this. Or, I mean, you could just have a real simple drive shaft. So you have a universal joint here, or a Hooks joint. We'll even put some splines on it so we have a nice slip joint there. Does everyone know what I mean when I say drive shaft? No? Yeah? Okay. If you look at your automobile, if it's rear-wheel drive, as the rear axle goes up and down, articulates, the distance from the back of the transmission to that rear axle changes a little bit. So you got to have something that'll take up that geometry. So you'd have a drive shaft. If you have a front-wheel drive car, you have that same argument, but now at each tire, right? So you're going to have to have something that deals with that. If we were to fix this and apply some torque here, we have that. And I've said this before, this is not just a mechanical subject. The civils can get into this if we have maybe some sort of a sign column here, and because of property lines or setbacks, utility easements or whatnot, maybe we have to build our sign like this, and if the wind blows on this thing, that's going to create quite a torque around here, isn't it? Okay, if this is a rigid sign, and you get the very similar loading with that. So whether we're looking at this portion right here, or that portion right there, or that portion right there, or that portion right there, whether the shaft is solid or hollow, we can learn quite a bit about this. I'm going to start talking about this from a standpoint of having a solid shaft, but eventually we'll see the virtues of having a hollow shaft and go from there. So in general, if we look at the cross-section of this, whether this is the cross-section of a screwdriver or the cross-section of a drive shaft, that shear stress would be carried across the entire surface like this. Okay, probably not uniformly, but it would be carried across the entire surface. And if I were to quantify that a little bit, let me draw this a little larger. And I could talk about these stresses. I could say that I'm going to have probably the largest stress at the extreme edges. And then it's actually going to be linear across the cross section. So I might talk then about some intermediate point. So I'll put a little differential element here, and I'm going to call this dA. And I'm going to say that that is out at some distance rho. Okay. And I'm going to say that the radius of this entire thing out to there is given as r. Okay. So I could talk about this shear stress here. I could talk about that as tau sub r. Whereas if I wanted to talk about this shear stress right there, I could talk about that one as tau sub rho. Tau sub rho is the shear stress at the distance rho out from the center. Tau sub r would be that extreme shear stress out at the extreme edge of this thing. And if I talk about the differential torque, so let's say dt, that's just really going to be a force times the lever arm or the moment arm, right? Really force times distance. So we could say that this thing is, let's see, force. I could take tau sub rho times dA. If I took the stress and I multiplied it by the area, that would give me force, wouldn't it? And the distance that it acts over is what? Rho, isn't it? Okay. Now, I'd like to probably express tau sub rho in terms of r. So, let's see, by ratio and proportion, I could say that this is equal to what? Rho over r times tau sub r?
Is that tau sub rho in the force step?
Yeah, this is sub in the equation here. Okay. Because I'm really just looking at a couple of triangles. I'm looking at a triangle, a smaller triangle here versus that larger triangle there. So this is by similar triangles. So let me make that substitution. I could say then that this was tau sub r divided by r, and then if I have a rho there and a rho there, I'm going to have rho squared, right? Times dA. So if I talk about then, this is the torque on that element. Or rather the torque supported by that element. If I look at the total torque, so looking at the total torque, I could say that that was T, which is going to be the integral over the area of dt, right? So I'd have the integral over the area of, do we have dt? Yeah, we've got that. That's tau sub r divided by r times rho squared dA, right? Everyone's okay so far? Let's keep working on our derivation then. So we had this expression right here. And let me rework that a little bit more. I think I can take the tau sub r and the r out because they should be constant. So I'm going to have tau sub r divided by r times the integral over the area of rho squared dA. Okay. Have you seen something like the integral of x squared dA or the integral of y squared dA or something like that? We actually saw that as we were finishing up statics. Okay? And that became known as the area moment of inertia. Now this is a little bit different because I'm looking at the rho, which is the distance from the center. So I could say that this is the polar area moment of inertia. Okay. If we were worried about, if we took something and we were worried about it bending about this axis, we might talk about IX. If we were worried about it bending around this axis, we might talk about IY. If we were worried about it twisting about that, we could talk about the polar moment of inertia. So, and IX and IY actually relate to this. So we're going to talk about the polar moment of inertia being equal to, a lot of times people will use the symbol J for this, or they might use the polar moment of inertia as I sub P, which would be equal to, actually, if we look at this, IX plus IY. So those values that we calculated in statics when you're looking at those cross-sectional properties, IX and IY, are actually related to that polar moment of inertia. If you want to do some in-depth studying on this, you can look at Appendix A in your textbook. Talks about not only the calculation of IX and IY, but the polar moment of inertia. If we look at units on this, the units on this are going to be distance to the fourth, because you've got distance squared times area, so you're going to have inches to the fourth, or meters to the fourth, or usually not feet to the fourth or millimeters. Usually the most common would be inches to the fourth or meters to the fourth. And I won't belabor this too much, because usually we look at and we derive this for circular objects, okay? And if we look at the polar moment of inertia for that, it's really pretty easy. We would say that it'd be equal to pi times r to the fourth divided by 2. A lot of times we don't have r specified, we have the diameter specified, so maybe we should talk about pi times the diameter to the fourth divided by 32. Okay? So those are two real common values for the polar moment of inertia for a circular cross-section. You might say, well, what if it's hollow? Well, we're just going to take the hollow portion and subtract it from the larger non-hollow portion. And we'll go through that in a future calculation. Let's see, that should give us the right units. Yeah, it does give us the right units. So if I recognize then that this is the polar moment of inertia, I could go back to this torque and say that it was tau sub r divided by r times the polar moment of inertia. Let's call this I sub p. So if we wanted to solve for the torque, not the torque, but the shear stress, tau sub r, we could say that that was what? The torque times r divided by the polar moment of inertia. And if you wanted to, I mean, this is probably the one that I would remember. If you wanted to, you could do this for tau sub rho. You would just take the torque and multiply it by rho instead of r and divide by the polar moment of inertia. But I think this is probably the most common one that you'd want to look at. If I do a unit analysis in this, if torque is in pound inches, which may seem a little unusual, oftentimes we're given torque in pound feet, but if I convert it to pound inches, and the radius is in inches, and then what do we say the polar moment of inertia would be? Probably inches to the fourth. I get units of what? I get to cancel that and that with a couple of those, and I get pounds per inch squared, or PSI, right? So the units do work out on that. So if you have one of these examples, a shaft that you're transmitting a torque with, and you want to know what the shear stress is due to that, you take the torque, you multiply it by r, and you divide by the polar moment of inertia. And I don't want to gloss over the units too much. This is probably worth a note here, because a lot of times we'll have the torque in pound feet, and you'll have to do a conversion. So the units work out very nicely if it's in pound inches, though. Questions with that? Well, I want to talk a little bit longer and land the concept of deflection, torsional deflection, because I think you recognize, maybe not so much with a screwdriver, although if the screwdriver has a particularly long shaft, you might recognize that with an extension. Have you ever seen an extension that's maybe a foot or two long, and it tends to have a lot of twist, right? Okay, anyone ever worked on their car or something? Okay, great. Yeah, if this distance is significant here, a lot of times you can begin to feel that twist, can't you? Okay, so we want to talk about that angle of twist. I'm going to draw a picture and probably clutter it up, so you may want to draw it fairly large if you're taking notes. So I'm going to look at a section of shaft here. Let's say this is fixed. And we're going to apply a torque to this thing. I'm going to apply the torque like this. Remember, I'm using the right hand rule. So if we had a shaft like this and we were applying a torque like this, and then we had this torque like that, what would that look with the right hand rule? What would that look like? We can represent that in a more two-dimensional fashion. You take the fingers of your right hand and put them in the direction of the torque, and then your thumb is pointing in the direction of that double arrow. Likewise over here, you'd have this. Remember when we did that in the first week when we were talking about internal loading? Okay, so I will talk about this. So essentially that's a torque using your right hand. That's a torque that is twisting this clockwise if we were standing here and looking at that. Okay, so you could imagine if we were to draw a line on this thing then, if we were to try and torque that clockwise, this line might twist, right? And might take on a shape that looks something like that. And I'm going to say that this angle in here is given as phi. Okay? So the angle of twist is phi. Okay, like that. And if I were to look at an element, let me say draw a couple parallel lines on this thing. And if I were to draw an element on this, the element here would be square, wouldn't it? Whereas the element here would be actually racked. This element would be a nice square element, whereas this element would be racked out of shape. Okay. So we could talk about this as a line that represents T naught. We could talk about this as a line that represents T final. Maybe you've even seen this on drive shafts. This is always if you go to buy a car, they usually use a tubing that has a seam on it. And if the seam runs down like that, that's probably a good sign. I've actually seen drive shafts where the seam went around this thing. Okay? That means it was probably not just driven to church on Sunday. Okay, if they've twisted the drive shaft that much. Okay, when we talk about twisting this thing, we're only going to be talking about a couple degrees, and we're going to be in the linear region, a couple degrees at maximum. We're going to be in the linear degree region where it goes back. But you can twist those shafts pretty substantially. So, well, let's see if I can come up. Let me put this angle here. I'm going to say that this angle is the angle gamma, because that's how much our element has twisted. So if I want to talk about the tangent of gamma, how did I say that would be if I were to look at this long triangle here, where this has some length L, I could say that the opposite side, what's this opposite side here? Well, if this has some radius R, the arc length of here is R times the angle of twist phi, right? Isn't that arc length that I've given? This is R times phi. And I'm going to have to divide by the length of the shaft, which is L. That's effectively looking at this triangle here, this very long triangle that I have drawn across there. And we said that we were going to look at a small angle. So this will drive the math people crazy, but it's really pretty sound. So for small angles of gamma, if gamma is pretty small, under 5 degrees, under a couple degrees, and we're talking about rotating a drive shaft or something like that, it's not going to be very large. If gamma is pretty small, we can actually just say that the tangent of gamma is really equal to gamma, and we get R times phi divided by L. Okay. So that's an important conclusion, and probably the process that we went through is the most important thing. If you start looking at something that's made out of some sort of putty or something, and it's rotating 500 degrees, this is not a good equation anymore, right? If you're looking at things like concrete or steel that are only going to rotate a tiny little bit, there's probably a very valid analysis. Well, the reason that I wanted to look at that is I wanted to go back and I wanted to look at Hooke's law for shear. And remember, that was to say that the shear stress tau was equal to the shear modulus of elasticity G times the shear strain gamma. So we now have something for the shear strain gamma, don't we? And we just finished up with tau. Didn't we finish up with tau? Where was that? Page 6. Yeah, right there. This thing right here. So tau is the torque times the radius divided by the polar moment of inertia is equal to G, the shear modulus of elasticity, times gamma. We just found gamma could be approximated, and is really a good answer if we have small angles of twist, which we're hoping we do, R times phi divided by L. So what I'd like to do is I'd like to solve for this angle phi. So I get to cancel the R's, and I come up with phi is equal to the torque times the length L divided by G times the polar moment of inertia. Okay, and that's probably worth putting a box around because we've come up with the angular twist for that shaft, and previously we came up with the stress. So we can talk about not only what the stress is, but what also the deflection is going to be. Let's look at the units in this. The units in this is, again, I might use pound inches, and maybe I'd better have the length in inches, which those, a lot of times we'll have those in pound feet or in feet, so you have to be really careful with the units, but if we're in pound inches and inches, and then G is going to be in PSI, pounds per inch squared, and I is inches to the fourth. I get to cancel this with that with a couple of those, and those with the other ones, right? What do you come up with? No units, which is what? Radians for our angular measure. Okay, so we got that angle of twist phi in radians. Okay. Well, this angle of twist, this is really acting, I mean, this is like a torsional spring, so I'd like to maybe look at this equation just a little bit more. So we've got that from phi being equal to the torque times the length divided by G times the polar moment of inertia. And remember, we'll derive this pretty shortly, but G is going to be equal to Young's modulus divided by 2 times 1 plus, or the quantity 1 plus Poisson's ratio. So we got a handle on that. But I'd like to look at this in a little more detail and solve for T. The torque T, I could say, would be equal to G times the polar moment of inertia divided by L times the angle of twist phi. And this actually then gets us back into something that looks like Hooke's law, right? Where this term here is really the stiffness, isn't it? We could say torsional stiffness. So if we have a torsion spring, do we ever have torsion springs? Yeah, a lot of suspension uses torsion spring. We put a torque on that. Okay. Even a coil spring, if you think about a coil spring, how a coil spring is built, when this, if I look at a piece of this coil spring, if I pull a piece out, it actually looks a lot like that, doesn't it, as that coil spring compresses? So yeah, a coil spring is really just a torsion bar that's wound up so we can put it in a little different space or a little different geometry. So torsion bars are used a lot in suspensions and design, things like that. So the stiffness, if we increase G, which is increasing some of these quantities, is that going to change the stiffness? Sure. If I go from an aluminum spring to a steel spring, that'll definitely change the properties. So that makes sense. What if we change the polar moment of inertia? If I go from this torsion bar having a cross-section that looks like this to a torsion bar that has a cross-section that looks like that, change dramatically. A lot of times people will talk about sway bars, and they'll talk about going from a 1-inch diameter sway bar to a 1 1/8, and you might think, well, that doesn't make much difference. But remember that what are we doing for the polar moment of a calculation? That is r to the 4th or d to the 4th. I mean, we handle those a little differently, but we're taking that dimension to the 4th, aren't we? Okay? So when you start taking those small distances to the 4th power, that can have tremendous implications. And what about the length? If this torsion bar gets longer, what's going to happen to its stiffness? It reduces, right? And that goes back to why we started this conversation talking about this good old extension on our socket set here, right? Has everyone seen a socket set? You know, you got to change, get to a bolt way down there. You get a really long extension and put a socket on the end of this thing. And if that's 2 or 3 feet long and you start to really put some load on this, you can actually feel it twist, can't you? And sometimes you can use that as a technique to undo a stubborn fastener, right? You just twist it up and all of a sudden it lets go, right? Yeah, hopefully for the best. So as the length increases, the stiffness decreases. So hopefully that makes sense. Well, what we will do when we get together next time is we'll start to look at what happens when I look at hollow shafts. A lot of you might say, well, I've got a drive shaft and it's hollow. What's going to happen there? There's a lot of lore and whatnot about this, that it's more efficient because you have 2 surfaces to bend on it. It's technically not more efficient. We would say it was way more weight efficient, because if we go back and look at our original picture that we looked at, the center here does not do a lot. So we actually get rid of that. So we'll look at some examples of some hollow shafts and see how they can be quite a bit more efficient from a weight standpoint. So that's where we will go next time.